Let's talk about graphing polynomial functions. We are going to be using the zeros of the function, the end behavior, the y-intercept, as well as finding some other points to kind of round out, but we'll be doing a bunch of graphing today. Here are a few guidelines to remember as you're going through and graphing. So our first step is to find the end behavior. So if we can figure out what the ends are doing, that helps us actually determine the directions of our graph. Number 2, find the y-intercept. Number 3, find the zeros using any combination of factoring, quadratic formula, or the rational zeros theorem, also known as the rational roots theorem. And then step 4 is to use all of these different things, as well as the multiplicity of each zero, and some other points to actually sketch a smooth continuous curve. So let's talk about the end behavior to start with. When we have the end behavior, this all depends on the degree of the polynomial as well as the leading coefficient. And if you recall, way back when in previous math classes, every polynomial is written as ax to the n plus bx to the n minus 1 plus c x to the n minus 2, and on and on and on. N being our highest exponent, and then it numbers down. So this right here is going to be your leading coefficient, and our highest exponent is our degree. Those are the two things that we're going to use to determine the end behavior. So if our leading coefficient is positive, so if a is positive, and our degree is even, that means 2, 4, 6, 8, our end behavior is going to be up, up. Which also helps us because if our leading coefficient is then negative, all it does is reflect it across the x-axis or do a vertical reflection, our end behavior would then be down, down. If you were to think about this, an example for up, up could look like this, and it could be crazy as long as the ends are pointing up, or it could be just something as simple as a parabola. Down, down, as long as the two ends are pointing down, we're good to go. Now, if our leading coefficient is positive, again, but this time our degree is odd, so 1, 3, 5, and so on forth, it's got a down, up end behavior. And then if our leading coefficient is negative, it just reverses, so it's up, down. So down, up, we can see this just with a linear, so we kind of know a positive slope, so x to the 1, or it could be like a cubic, so x to the 3rd or x to the 5th or something like that. So it starts down, ends up, and then up, down just goes in reverse. So it starts up and ends down. All right, for y-intercept, anytime you are on the y-axis, our x value is 0. So if we think about here, this is our x-axis, this is our y-axis. If we are on this point, that means it is 0 and then some value, which would happen to be our y-intercept. So if x is 0, we just plug 0 into the x's to find our y-intercept. All right, now our zeros, these are also known as the x-intercept. So this is where it's hitting on the x-axis. So if it has an odd multiplicity, meaning it happens 1, 3, 5, or so on times, what this does is we say it passes through. So it passes through the x-axis. So if I have my graph here, let's say I have x minus 1, x minus 3, and we're going to say this is to the 3rd power. That would give us a multiplicity of 3 on that one. And we'll just call that a day. So that means our x-intercepts are 1 and 3. And depending on what else is happening now, like here I know this is going to be down up because our leading coefficient is positive. We're going to pass right through those x-intercepts. And then we use our other points to actually determine what's happening around those. We have an even multiplicity, meaning our 0 happens 2, 4, 6, or so on times. We say this bounces. For example, if I were to have x plus 2 squared, x minus 1, we'll go with those. So this one happens twice. So I'd have x equals -2 that has a multiplicity of 2, and then I'd also have x equals 1 that just happens one time. So once again, depending on some other factors, this one is going to be an odd degree, so it's going to be down, up again. So at -2, I have an x-intercept, and at 1, I have an x-intercept. That means at the -2, it bounces. So since I know it goes from down to up, I'm going to say it bounces right here, and then this one's going to pass through. And once again, we use our other points to kind of determine this. And I'm going to do an example here so you'll actually see how this all plays out. So let's get to our example. And once again, knowing your guidelines for graphing is a great way to start. So our first thing that we're going to find is the y-intercept. Remember, to find our y-intercept, we plug 0 into all the x's. That means that I'm going to have a 0, a 0, a 0, and a -12. That makes our y-intercept -12. All right, let's find the end behavior. All right, to know this, our leading coefficient, we can see our leading coefficient is a -1. So we're going to say our leading coefficient is negative. And our degree happens to be 4, which is an even number. So we're going to say our degree is even. So if our leading coefficient is negative and our degree is even, I can look at that chart and see that my end behavior is going to be down, down. And the next thing we need to find are the zeros, also known as the x-intercepts. This is where you can use factoring. You can do the P's and Q's, which is our rational zeros theorem, which is what's going to happen here, to actually find those zeros. So it's kind of a refresher for our rational zeros theorem. P comes from this constant, and Q comes from our leading coefficient. So all the factors of P will be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. All the factors of Q will just be plus or minus 1. So P divided by Q, so all of our possible rational roots will just be all of these divided by 1, which will just be plus or minus 1, plus or minus 2, 3, 4, 6, and 12. And then we'd go through and actually figure out which of these give us zeros. And we've used our calculator to do this in the past, which is 100% fine to do this again. So using our calculator, we are going to get x equals 2, x equals -1, x equals -3. And let's see what else we can come up with. And you may only find 3 of them to start with. And our degree up here tells us how many we should have. We should have 4 zeros. Whether they're all rational, real, or not, that is left to be determined. I have 2, 3, 4, and -4, 6, -6, 12, and -12. So right now, I'm not finding them. So I've got 3 of my 4 zeros, which means now I'm going to do synthetic division. So I'm going to I'm going to kind of shrink these out of the way a little bit. That way we have some room to work. All right, synthetic division. We're going to start, it does not matter which of these zeros you start with. We're going to start and put one of them in our box and do our synthetic division. So we'll have -1. So 4, and I got to count down my exponents because remember, if I'm missing a term, I have to put a 0 in that. So I have a 4th power. I have no 3rd power. I have a 2nd power. I have a 1st power, and I have a constant. All right. And then my remainder is going to go down here. Now, we found these to be zeros, which means my remainder should be 0. So let's test it out and see. So we have -2, -4, 5, 10, 6, and 12 is 0. So we got our remainder of 0, so we don't need to worry about that. But what we can do here is do our next one. So I've got my next 0, and I'm going to just do it again. My remainder is going to be under the 6 this time. So drop and multiply. And once again, I got a remainder of 0. So that worked out good. And now I can do my last one, which would be a -3. And my remainder is going to be down here under the 6. So -1 is 3 is 2 is -6 is 0. All right, let's count it down. So here we have an x to the 4. That makes this an x to the 3. This is an x squared. And this would just be an x. So my factor I have left would be a -x plus 2. And if I set that equal to 0, I'll end up with x equals 2 again. So notice I already had that. So what that tells us is this specific 0 has a multiplicity of 2, which is an even number. So let's go through and actually graph these and figure out what points we can put on here. All right, first thing we have to do is get an axis on here. I want to be able to see the entire graph. I'm going to send this to the bottom layer so I can actually draw on it. Alrighty. Let me start this one down here. And then let's see, my zeros are negative, so it really doesn't make a huge difference. We may do it over here. All right, I did get a y-intercept though of -12. So let's see how I did as far as like graphing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I might go by 2s, but remember if you go by something other than 1, you need to label it. So -2, so this would be a -4, -8, -12, -16, and -20. So I'm going by 2s, I just want every other one. And then going up, I would do the same thing. So 4, 8, 12, 16, 20, 24, 28, 32. And because my x-intercepts are fairly small, I shouldn't have to do anything other than 1s. So I'll go by 1s, but I'm going to number every other line. So it looks like I'm going by 2s, but I really am going by 1s. -2, -4, -6, -8, -10. All right, let's actually graph this. Let's graph all the things that we have and put it all together. So our y-intercept is -12. Our end behavior is down, down. That means on this end, I should be going down, and on this end, I should be going down. All right. My zeros, I have a 0 at 2, -1, and -3. That means these two have an odd multiplicity. So since I'm starting down, I know this is going to kind of go up through that one and come back down through this one. And since this one has an even multiplicity, it's going to bounce. Now, that's not an exact graph, but it's pretty close. So now I'm going to get some other points to round this out. -2, where x is -2, is going to be a big one that I want to have. So let's see. Where x is -2, my y is 16. All right, let's try -4. -4 is a -108, which means it does not cross this -4. So I'm going to try and draw this, and this is really hard on the computer. So this is almost going straight down, and it's not hitting that other side there. This is coming up, hitting this, and coming back through here to 12. And let's see what we get at 1. So at 1, we're at -8. We'll kind of bounce back up here, and then maybe let's see what we get at 3. 3 is a -24, so once again, I don't have enough space, so this is just going to kind of come down. And there's our graph. The important thing is being able to make sure you can see your entire graph. If you start graphing and realize, hey, my points don't show up on my graph, you'll have to redo the y and x scale just so things start to show up. You want to see the entire graph. Let's try another example. This one's a much higher degree, but it's going to work the exact same way. And in fact, what I'd recommend doing is maybe pausing and you trying working through the entire process, and then start this back up so you can see exactly what we did and see if you agree. All right, so the first thing we're going to do is we're going to find the y-intercept. Once again, if we plug 0 into the x's, all the terms with the x's go away, which means everything went away, so our y-intercept is 0. Our end behavior, our degree is odd, and our leading coefficient is positive. So our end behavior, if you look at that chart, should be down, up. And now we're going to find the zeros. Before starting though, I look at all this and I see, hey, there's a whole bunch of x's here. I'm going to factor that out. I can factor out 3 of them before we ever start, which gives me 4 minus 4x to the third plus 7x squared minus 12x plus 12. And you may be asking, why do we do that? Well, right here, I already found 3 of my zeros. X equals 0, and since it has a cube on it, that's a multiplicity of 3. So I found 3 of the 7 total zeros I'm looking for. Once again, I'm going to do the p's and q's. Since q is 1, all I have to worry about is the p's. So p over q will have plus, it'll be exact same as we had on the last problem. So 1, 2, 3, 4, 6, and 12. And then we go to our calculators and see if we find any of our zeros. So give me a minute here to do that. All right, so once again, I got x equals 2. All right, and that's the only one I got. So that'll be interesting. We'll try and see what we get out of this. So let's put 2 in our box and their coefficients. So 4th power, 3rd power, 2nd power, 1st power, no power. My remainder is going to drop under that one. All right, so drop the 1. We've got 2's, -2. And we're just going through and doing our synthetic division here. Hey, look, we got a 0. All right. What we might try here is, I just want to see if this one shows up again. So I'm going to do it again, and if my remainder is 0, it has a multiplicity. If my remainder is not 0, then it doesn't work, and I'll have to come up with a different way to factor that, which is fine. We definitely can look at that. But let's just try 2, because I didn't get any of the others to work, which means 2 might happen more than once. So there we go. We got 2. 0 is 0, is 3, is 6. Hey, look at that. It works again, which means automatically right here, it happens twice. It could happen again, but I kind of don't think so. I'm going to go ahead and put a multiplicity of 2 on that one. And let's see what we have left. So this one was an x to the 4th, an x to the 3rd, and an x squared. So let's see what our remaining zeros are going to be, because I'm still looking for, I've got 5 and I need 7, so I'm looking for 2 more. So I have an x squared plus 3, and I'm going to set that equal to 0. So subtract our 3. So x is going to be plus or minus, we're square rooting a negative, so we have an I square root of 3. There's our other two zeros, but those don't show up on our graph, so we don't have to worry about those. So let's go back and graph the things that we have. So my y-intercept is 0, so I think I'm going to center as much as possible on this. I'm going to center the x and y axis. Okay, that's not centered, but I can move it here. That's probably a little better. All right, let's try graphing this. So my y-intercept is 0. My end behavior, that means this end should be going down, this end is going up. And the zeros are 0 and 2. So I've only got 2 zeros on this one. All right. And let's see, we're going down and up. So if this is my last time it crosses, that means it ends up. So this is going to bounce because it has an even multiplicity. And this one's going to pass through. Because they've got to kind of connect somehow. And this one ends down and it won't cross the x-axis again, so this side has to be down. And the reason we know it won't cross the x-axis again is because we would get another 0 over here if it did. So let's get some points to round this out. I would say let's definitely see what's at 1. 1 is at 4. So we could actually go by ones probably. And sometimes I check the in-betweens just to make sure we're not going over. So I tried 1.5, and 1.5 is actually at 4.4. So it's kind of up here. So sometimes you might just check that. 0.5 though is less than, it's like 0.91. So it's like right in here. And let's try -1. -1 is -36. So we're definitely not going to get that one. 3 is at 324. So we're definitely not going to get that one. So doing our best. This one's almost going to be, yeah, that's not very straight. Let's try this again. So it doesn't cross, but this one does kind of come up and go like this and then bounce back up. And this one's like 320, 324, so it's way up there. And it should be a little straighter than that, but it's really hard to draw on our computer. And so that's what that graph looks like. And here's the other thing you could do is, let me pull up Desmos. We can kind of see how we did. The hardest part is typing all this in because it's a lot. So I've got x to the 7th minus 4x to the 6th. I'll pull it over so you can see it here in a second. 7x to the 5th minus 12x to the 4th plus 12x to the 3rd. All right, I'm going to pull this over here. So this is what this graph is looking like. So it's almost shooting straight up, and here it's heading down pretty solidly. Yeah, so here's 1, so it didn't cross our 1. So we can see it does go up to just above 5 at 1.3, but without actually doing some additional work, and that's where calculus comes in a little bit later, we wouldn't be able to determine that exact value without a bunch of trial and error.